From Illinois Public Media, this is the 21st Show. I'm Brian Mackey. According to the U.S. Department of Agriculture, corn is Illinois' top crop. This will come as no surprise to anyone who's driven the endless miles of our interstate highways. And when you think about what happens with modern corn, how could it not be number one? It's, of course, eaten as a delicious vegetable. You can find other uses for it. It's eaten secondhand through the livestock that it feeds. There's also the many products sweetened with high fructose corn syrup, and it's used in ethanol, the fuel additive. One reason that corn has been so successful here in the 21st state is the science behind hybridization, which allows farmers to ensure a high yield that can survive the harsh realities of extreme weather, pests, viruses, and other threats. But new research from the University of Illinois Urbana-Champaign suggests that the way we've been using these hybrids could be setting up problems in the future. Joining us now to talk more about their work, we're joined by three researchers from the U of I's Department of Crop Sciences. Camila Godoy dos Santos is a postdoctoral researcher. Alex Lipka is a professor of biometry. And Martin Bone is a professor of maize breeding and genetics. Camila, Alex, Martin, welcome to the 21st Show. They're joining me in studio today. Thanks for being here.
Very glad to be here.
Yeah, it's awesome.
And listeners, you can join us as well at 800-222-9455. That's 800-222-9455. Martin, I'm going to start with you, and maybe we can begin by talking about the corn that we do grow in Illinois. What is the typical breed we use here in modern agriculture?
So the corn that we are using here is the corn belt dent, and this is a corn variety or family of corn that moved in from was developed by several other families of corn that moved in from the east and so the canonical story tells us that there was the southern dens in the southeast of the U.S. and then the northern dens in the northeast of the U.S. And with settlers, these corn families and populations moved into the Midwest, and here they started to hybridize. And sometimes farmers recognize that by crossing some families of these different groups. The southern dens, reed was one of these important populations within that group, and from the north, from Pennsylvania, the Lancasters, for example, when they cross these and they recognize that there is hybrid vigor, they can create something that produces more than the parents that were crossed with each other. Then I think the modern concept of heterotic groups is developed in after the Second World War, when people wanted to wanted to utilize that concept in hybrid breeding. They developed inbred lines, and then they recognized that crossing inbred lines from these different families, created hybrids that were highly productive. And some of these modern heterotic groups that are used, these genetic families that are genetically different, are the stiff stalk.
I'm going to ask you to pause on the stiff stalk versus the non-stiff stalk. We'll come back to that in a little bit. And Alex, let me bring you into the conversation. Talk a little bit more. And sometimes I say, this is not a college class. Talk to me like I'm, a smart 13-year-old and help me understand why this specific method. It sounds like maybe there were some accidents that, farmers sort of intuiting and understanding this stuff, and now there's science behind it. Why are these methods what we're using to, create corn in 2026?
Okay, so everything Martin was describing, you can think of developing two different boxes of Legos, okay? So one of these heterotic groups is a bunch of mom plants, and then another box of Legos is a bunch of dad plants, right? So then you pick, breeders can pick your favorite mom plant, your favorite dad plant, cross them, you have an F1 offspring, and then they produce, they yield much better than what you would expect from your from like the contributions of each Lego alone.
Okay, so that makes sense, and I think that would work with my son. Camila, let me bring you into the conversation. So the corn, we've talked a little bit about the corn we're using today, how it developed. With that in mind, can you say more in detail about what your research found about some of the potential problems here? And again, keeping in mind, like you're talking to a smart teenager.
Yeah. So the idea of our work was to check if this two population of lines that we have, if these have generic variation. And for this, we develop different type of models. Sorry.
You can have a glass of water if you need. Yeah, take a drink of water. So you were saying that you develop these different types of models to see if there's genetic variation. You're good to go. Yeah.
Yeah. So with this model, we saw that we don't have generic variation across the stiff stock lines across this population. And this is a critical result because stiff stock population is the most important heterotic group in the Corn Belt. And we perform a different type of traits, and the generic variation was gone for the grain yield, the most important trait. So for the most important trait and the most important line population, we found that we don't have generic variation anymore.
Okay,
Yeah.
so you're lacking some of this genetic variation, and I guess, Martin, let me come back to you then. What are some of the consequences? I guess maybe a more basic question, is there a new corn sort of breed every year? I mean, is this something that's constantly evolving, not evolving in the sense of evolution, but constantly changing to keep up with, insects and new pesticides and things like that?
I think this is the business model of the breeding industry, isn't it?
That
I
too.
think
Yeah.
they are developing new inbred lines within these heterotic groups every year, and they try to combine the positive traits within each of these inbred lines that they then transfer into the hybrids by crossing these inbred lines with each other. And I have to come back to this Lego model that Alex talked about. If you have a lack of genetic diversity, if you have only red Legos within of a certain size in your toolbox,
that 4x2, the classic 4x2 Lego.
Yeah, exactly.
Yes.
And it's red, then you are lacking the variance, you are lacking the combination that in your toolbox that allows you to adapt to future environments. And I think we need to recognize that we have to make decisions now with regard to the development of our inbred lines and germplasm and heterotic groups, if we want to develop inbred lines for future environments for the next 20 or 30 years. We are making decisions now, and if we and we recognize with our study that for most of the corn, specifically for the non-stiff stalks, we have all the genetic diversity that we need in order to improve that heterotic group and to bring that side into our hybrids. However, for the stiff stalks, as Camila said, particularly for the stiff stalks that we utilize here in the Midwest, we are lacking the diversity. We are not able in the future to adapt to things that will change. We already experience, isn't it, that the weather is changing, it's getting more extreme, more flooding, it's getting hotter. With this, more insects are coming in, more diseases are coming in. We have to future-proof our hybrids by adding or keeping up the genetic diversity that we have.
I kind of interrupted a little earlier when we were talking about stiff stalk versus non-stick stalk. So maybe, Alex, I'll come to you, and if you can just say a little more about that. So I think stiff stalk, it's sort of intuitive. You're driving down the highway, you see all that corn lined up, perfectly aligned. I remember I was actually talking with the state's Department of Agriculture director this week about some of the storm damage, and he said, sometimes that corn, it just kind of pops right back up, the stiff stalk stuff. What is the difference? What are we eating? What are we feeding to our animals? What are we putting in our gas tanks? What is that? Yeah, talk more about this stiff stalk versus, I don't know if it's limp stalk or non-stiff stalk. What term we should use?
Right. So stiff stock versus non-stiff stock. So I'll say off the bat that my colleague Martin is definitely the expert on this kind of stuff. But the way corn breeding has happened, right? You kind of select your corn, like your Legos, into these different bins of like stiff stock versus non-stiff stock. So these are two different boxes, stiff stock, non-stiff stock, and then they just bred for, favorable traits. So I guess the appearance. And I remember, Martin, you saying the other day that stiff stock, they were selecting for this phenomenon you were describing where if it's windy, the plant will fall down. So they were selecting for making literally the stiff stock so it can be resistant to the wind. And non-stiff stock, I am guessing that they were selecting on something else.
Yeah, absolutely. I think you're absolutely right. So the stiff stalk, actually most of these or most important inbred lines out of the stiff stalk group were developed from the Iowa stiff stalk synthetic. And my colleague John Sprague, in the 30s, I think, he had the idea to develop these a population. We call this a synthetic that is particularly bred for stiff stalks. And he combined 16 inbred lines. He selected these for their stalk traits and root traits, and then out of these, mixed them together to form this population and improve this over time. And out of these different cycles of improvement of this synthetic, important, really, really important inbred lines were developed that are reused constantly, and their offspring are reused constantly. And this is the problem. This is a genetically narrow base. And from this base, we are selecting inbred lines. And often these well-performing inbred lines out of the stiff stalk heterotic group are all related. And so that is...
Because it makes money year after year.
Yeah, exactly. Yeah.
It's reliable.
And
yeah.
You're absolutely right. We know that they are good. So therefore, we are reusing them. But using then also modern technology like genomic selection, and Alex and Camila, they are the experts in genomic selection. This is making our breeding program so effective and predictable that we are draining the genetic diversity very quickly.
So Camila, how do you determine this? I mean, are you getting dirt under your fingernails? Do you have to do this season by season? Is it computer modeling? Are you peering into a microscope? What does this actual work of doing this research look like?
Oh yeah, actually, we already had the field data and the genetic data. So what I did was use this data and try to develop model to transform the data in a biological meaning. So using, for example, the genetic information of the parents, I was able to predict the hybrids. And I use that information to get accurate models to answer all these questions that we have, because, we need to understand if that population has genetic variation. But for that, we need to develop good models to have this answer in a accurate way. So I try to put together all this information into a model and collect the information and this answer. Yeah, and actually this work was developed in two parts. The generic variation was the first part, and the second part was about genomic selection, because we use the same model to predict hybrids using the parents' information.
Using the parents' information.
Yeah.
Okay. We're going to need to take a break here in a second, but I guess just briefly, and maybe Alex, you can just outline, what are some of the potential challenges? I mentioned climate change is one. What are some of the other things that we might be worried about, in just like maybe 30 seconds? Give us a quick list of some of the problems that, could come up.
Yeah. So, climate change, absolutely. also, this loss of genetic diversity. Like, how can you increase more Legos into that box of parents?
Why do we need to, though? What do the Legos solve for?
So imagine that you have hybrids and they all essentially have the same mom, right?
Yep.
So if a disease comes in and all of these hybrids are susceptible to the disease, you'll have one less tool in your tool set to combat that. And worst case scenario, maybe you won't be able to eat anymore.
Okay. Well, that is a great setup. We're going to take a break and we will talk. Is there a possible future where we don't have corn? Oh, my goodness. All right. We are talking about this with three researchers from the University of Illinois who have been looking into this idea of a lack of genetic diversity in our corn, which could make it harder to develop corn that can withstand some future threats. Martin Bone and Alex Lipka are professors at the U of I. Camila Godoy dos Santos is a postdoc researcher there. If you want to join us, 800-222-9455 is the number. We're going to continue after a short break, 800-222-9455. This is the 21st show. Stay with us. It's the 21st show. I'm Brian Mackey. I'm joined in studio today by three experts from the University of Illinois Urbana-Champaign's Department of Crop Sciences, and we are talking about corn genetics and potential issues they've been studying with the future development of new corn hybrids. This has to do with a lack of genetic diversity, which could make it harder to develop corn that can withstand potential future threats, such as climate change, viruses, pests. We're talking about this with Camila Godoy dos Santos, a postdoc researcher at the U of I, Alex Lipka, professor of biometry, and Martin Bone, professor of maize breeding and genetics. You can join us at 800-222-9455. That's 800-222-9455. So, Alex, what are some of the ways farmers can balance, the predictability they want? There's so many uncertainties in farming. If they can find something that they know works, a lot of farmers are going to stick with that, while also ensuring this, potential genetic diversity in the corn that they're, breeding and growing.
Yeah, so there are multiple ways to approach this. I think the simplest thing is, so Camila's research has shown that it's the training material for these genomic prediction models that really matter. You have to have your training corn have the same, genes, alleles, allele frequency, all that stuff as your predicted hybrids. So her results showed compellingly that if you include the parents, you're going to get more accuracy. So that's one route. Another thing is when you're doing this genomic selection, you're selecting on the genetic potential of a hybrid. Okay, so breeders, if they use genomic selection, they might select for the best maize hybrids. Well, you can also select on the variability of the hybrids, so you can make sure you're intrinsically including some genetic variation in your decisions. And Martin is on several projects that's looking into increasing genetic diversity into the heterotic groups themselves. That is, adding some more exotic Legos into your box of Legos.
Okay. How do you actually do that? And I don't know who wants to take this, Camila. What is that actually? What is the process by which this happens?
So I think the process is a lengthy process, and this is the reason why industry is often reluctant to do this, because they reduce the eliteness of their germplasm by adding foreign materials, exotic materials. So they have to build it up again. So here at the university, we are able to do this. We can do this in the long run, and
because it's not economical to test
absolutely
in the fields.
Yeah.
Okay.
Yeah, and then also to make these crosses, and it takes time to develop these materials. And perhaps a little example. So we are developing. So we recognize that our modern corn hybrids lack the ability to interact with their soil microbiome. So they are not recognizing what microbes are there, and then manage these according to their needs. And we've shown that early hybrids from the 60s, 70s, and 80s are able to do this. So we lost that trait. We lost that Lego piece out of our box, and we need to bring it back. And we recognize that we have to go back to teosinte, the undomesticated form of corn from Mexico, to bring back that trait. And this is what we are doing. And together with colleagues, we created crosses between modern corn and undomesticated corn, and over time developed these new varieties that again contain that little Lego piece that we lost, and we brought it back through that route.
I got to say, reading your research was the first time I'd ever been introduced to the concept of wild corn. I didn't even know that was something you could find in the world. I don't know if you can talk about that, and I understand that maybe, going back in generations and, bringing in grandparent corn or great-grandparent corn. Maybe, Camila, you can talk about some of that work as well.
Yeah, you can go back in this population because we have yield population, so that population can contain some genes for, resistance for disease and pest and disease. And we cross with the modern lines to try to get this resistance again. So, of course, because we have today elite lines. In a real breeding program, in a modern breeding program, we have elite lines. And, for example, the stiff stock populations, they are elite lines, and we can go back in these yield lines and make these crosses,
We got a question from a listener, Sonia in Decatur, who said, when did this idea for adding Roundup to the corn come up? And why must we do this? And I'm going to tease. We actually have coming up tomorrow on the show a conversation about pesticide drift and some people who have, some significant property next to commodity crop fields, and they're concerned. They've seen damage to their trees. They wonder about what it's doing. There's a school that was next to one of these fields, and the kids were told to shower after a cloud drifted into their playground one day. That's tomorrow's show. But Martin, maybe you can address some of, what is there value? I presume, since it's so wide, what is the good in Roundup? What are some of the downsides? Talk us through that.
So corn is transgenic, so it carries genes that protect it against the herbicide. So we can spray and manage all the weeds out of the cornfield without killing our corn hybrids. And this is a very effective way of managing these weeds. I have a breeding program for maize hybrids, particularly developed for organic farming systems. And when I talk to organic farmers, then managing weeds is on top of their list. They want hybrids that can, tolerate high weed pressure. And so in conventional agriculture, we don't have that problem because we are using Roundup. And whether it's very effective. I think there are some of my colleagues are working on Roundup glyphosate tolerant wheat populations, and so there are issues around this. But in terms of managing weeds, this is a very important tool for conventional agriculture. However, there's a lot of discussion going on. You mentioned with other pesticides and herbicides, there are environmental issues. People say there might not be environmental issues using Roundup, but there's definitely a large group of consumers that thinks otherwise, and there's some research that is not really conclusive. So I think it's a great question to ask, and a great question to ask to the industry whether there are alternatives.
Yeah. This is probably the last question we may have time for. You sort of teased this idea that we could have a future without corn, right? I was thinking of that movie Interstellar. I don't know if you saw this, about 10 years ago, science fiction film. set aside the part where they go to space. The reason they're doing that is there's some unnamed blight on Earth. Corn is the only crop left in that version of our potential near future. Could there be a future, and Alex, I'll send this to you, like where we don't have corn because of some of these problems that you all are studying?
I think potentially, but unlike Interstellar, I don't think it's the end of the world.
Okay.
I think, honestly, my philosophical thoughts on this is we need diversity of foods to eat. So, for example, I'm really interested in so-called orphan crops in Africa, and I think that if you put resources to such crops that maybe do not have as much, advanced genotyping and phenotyping, we can get more food available, and it's more resilient to any stresses that the next future decades will throw at the fields.
Alex Lipka is a professor of biometry. Martin Bone is professor of maize breeding and genetics. And Camila Godoy dos Santos is a postdoc researcher, all in the Department of Crop Sciences, the University of Illinois Urbana-Champaign. Thank you so much for being with us, sharing your work with us today on the 21st Show.
Thank you for having us on.
Thank
Thank you.
for
This was
having
awesome.
me.